Welcome everybody, I'm Ilias, and today I'm going to present our joint work with John, Prodromos and Ion on GreekBERT. So first of all, what is BERT? Why is it relevant to NLP and how does it work? In our case, we aim to train a model on modern Greek that will collect it and pre-process the Greek parts of the Wikipedia, the European Parliament proceedings, and OSCAR, a cleansed version of Common Code. Moving forward, we have to pre-train BERT from scratch, meaning that all of its weights are randomly initialized. We opted to train a model similar to the original BERT base. BERT is pre-trained on pair of sentences. Each sentence is represented as a sequence of subword units, while a special classification token indicates the start of the sequence, and the separator token indicates the end of each sentence. Some of the tokens in both sentences have been masked out. BERT is pre-trained in two auxiliary self-supervised tasks. The first one is called Masked Language Modeling, MLM in short, where the model tries to predict the masked out tokens based on the representation produced by the final 12 layers of BERT. The second task is called Next Sentence Prediction, NSP in short. On this task, the model uses the final representation of the classification token to predict whether the second sentence immediately follows the first one or not in the original corpus. Given both tasks, BERT learns to produce high-quality context-aware representations of both subword units. In case of the classification token, it learns to produce quality pairwise representations. The final step is to fine-tune BERT for downstream tasks. BERT can be trained for various tasks, for example, sequence labeling tasks like name entity recognition or classification tasks like natural language inference. While the original BERT-based model of Devlin et al. Was a monolingual English model, the authors also released a multilingual model which is pre-trained for 100 languages including Greek. To support all languages on par, the model uses a shared vocabulary of 100,000 subwords. The model is pre-trained on the Wikipedias of the 100 languages. More recently, LAMP and Kono introduced XLM, a multilingual language model pre-trained on the Wikipedias of 15 languages, including Greek. Contrary to MBERT, XLM omitted the pairwise classification task and introduced the translation language modeling task. TLM for short is a supervised extension of MLM, where each training pair contains two sentences from two different languages, where the first sentence is the translation of the second one and vice versa. Finally, Kono et al. Introduced XLMR, which further improved the results of XLM without relying on the TLM task by using more training data from Common Crawl and a larger vocabulary of 250,000 subwords covering 100 languages. A common drawback of all the affirmation models is the underrepresentation of the Greek language in their vocabulary, which is approximately 1 to 2% of the subwords that rely on the Greek alphabet. In parallel, many works study the use of monolingual language models and compare them with the multilingual ones. Martin et al. Released Camembert, a monolingual language model for French, and their model is similar to Roberto Flio et al., which means that considers only the MLM task. Similarly, Virtanen et al. Released FinBERT, a monolingual language model for Finnish based on BERT. Both of them outperform some of the multilingual models in several downstream tasks. Monolingual transformer-based models have also been released for several other languages, showing strong performance in preliminary experiments. The first downstream task is part of sys tagging, and we will use the Greek dependency stream bank published by Chalkidis et al. All sentences in the datasets have been annotated with post tags from a collection of 17 universal post tags. The second downstream task is name entity recognitions. Since there are no publicly available datasets, we will use two currently published datasets developed by Ioannis Daras and Angeliki Romanou. As both datasets are fairly small, we will merge them. Sentences may include the have annotated for persons, organizations, and locations. The third and last downstream task is natural language inference, and here we use the XNLI dataset published by Kono et al. This dataset consists of pair of sentences. Each pair consists of a premise and a hypothesis, and the task is to decide whether the premise entails, contradicts, or is neutral to the hypothesis. The dataset has been translated in 14 languages, including Greek. Across all benchmarks, we compare the newly introduced GreekBERT with MBERT of Devlin et al., both the case-sensitive and uncased version, while we also compare with XLMR of Kono. As we expect, it will perform better than the multilingual BERT based on the findings of the literature. We also experiment with established neural model operating on pre-trained word embeddings. In case of part-of-speech tagging and name entity recognition, we will use bioelastic CNN CRF of Meinhof, while in case of natural language inference, we will compare with the composable attention model of Parik et al. In most models, we use the publicly available Greek 300-dimensional fast-text embeddings of Vogianovski et al. As we already noted, the Greek language is underrepresented across all multilingual models. Given this issue, Greek words are often overfragmented. For example, the word kategorúmenos splits into 6 subwords. In order to estimate the level of fragmentation between all models, we will introduce the word fragmentation ratio, which is the average number of subwords per full word across documents. We observe that GreekBERT has the lowest word fragmentation ratio across all datasets, with XLMR being the second lowest with a large difference from both BERT models. We expect severe fragmentation will harm the performance of multilingual models, contrary to GreekBERT. Before moving to the experimental results, we would like to discuss another important issue. XNLI is a cross-lingual corpus, whose training pairs have been machine translated from English. Inspecting the dataset, we observe that many of those have been poorly translated from English to Greek, which may harm the performance of the models trained on such noisy data. Based on this observation, we want to assess the effect of using the full training set, including many noisy pairs, against using a subset of the training set containing only a few high-quality pairs. We estimate the quality of machine-translated pairs as the perplexity across text computed by GreekBERT as a language model, and retain the 40,000 pairs with the lowest average perplexity across the text. To further highlight this issue, we present a selection of samples, both in the translated form in Greek and a back translation in English. The pair in orange color is a random one, and obviously the text does not make sense. We observe that the second pair in green color, which is among the best ones according to GreekBERT, is correct, written in fluent Greek, while the last pair in red color, which is among the worst ones according to GreekBERT, is even worse than the random orange pair, containing even the misspelled half Latin, half Greek word. While the training set is noisy, both development and test data have been translated by professional translators. Thus, we can safely evaluate on the Greek part of the dataset in a monolingual fashion. Here, we present the results of part-of-speech tagging. All transformer-based models have comparable performance, close to 98% accuracy, with XLMR being marginally better than GreekBERT and MBERT. By contrast, bioelastic CNCRF performs clearly worse, but the difference from the other models is small, approximately 1%. The fact that all models achieve high scores can be explained by the observation that the correct post tag of a word in Greek can often be determined by considering mostly the word suffix, or for short function words, the word itself, and to a lesser extent, the word's context. Thus, even multilingual models with a high word fragmentation ratio are often able to guess the post tags of words from the subwords, even if the subwords correspond to suffixes or other small parts of words or frequent short words included in the subword vocabulary. Hence, there is often no need to consider the context of each word. We move on the results of name entity recognition. We observe that GreekBERT outperforms the rest of the methods by a large margin in most cases. It is approximately 9% better than bioelastic CNCRF, 4% better than the two BERT models on average, and 1% better than XLMR. The net task is clearly more difficult than part-of-speech tagging, as evidenced by the near-perfect performance of all methods in the former task, compared to the far-from-perfect performance of all models on this task. Being more difficult, the name entity recognition task leaves more space for better methods to distinguish themselves from weaker methods, and indeed, GreekBERT clearly performs better than all the other methods, with XLMR being the second best method. Further on, we conduct a pair entity type evaluation of the two best models. Both models are more accurate with predicting persons and locations. GreekBERT is better on persons, while models are comparable on locations. Concerning organization, GreekBERT is better, but most methods struggle. Inspecting the results, we observe that organizations often contain person names, for example, consider the entity Biskota Papadopoulou, or locations, consider the entity Athletic Bilbao, which is the core reason for misclassifications. Finally, we observe that GreekBERT is again substantially better than the rest of the method in natural language inference, outperforming DAM by approximately 10%, the two BERT models by approximately 5%, and XMLR by approximately 1%. Interestingly, performance improves for all models when trained on the entire training set, as opposed to training only on the high-quality training subset, contradicting our assumption that noisy data could harm performance. Using a larger training set seems to be better than using a smaller one, even if the larger training set contains more noise. We suspect that noise may in effect be acting as a regularizing, improving the generalization ability of the models. As in the previous dataset, we report results per class for the two best models. GreekBERT is better in all three classes, while both models have difficulties when predicting neural pairs. Inspecting the results, we observe that neutral pairs tend to be confused with pairs containing contradictions. So to recap, we present GreekBERT, a new monolingual BERT-based language model for modern Greek, which has been trained on large model Greek corpora and can be fine-tuned for particular NLP tasks. The new model achieves state-of-the-art performance in Greek, part of speech tagging, name entity recognition, and natural language inference, outperforming strong baselines in the latter two more difficult tasks. We show that XLMR, which is a multilingual model well trained in larger corpora based on a larger vocabulary compared to BERT comparable in most cases. We also show that shallower established neural methods operating on word embeddings are inferior than the multilingual pre-trained language models. Most importantly, we released the pre-trained GreekBERT model, code to replicate our experiments, and code illustrating how GreekBERT can be fine-tuned for NLP tasks. The model is also available from the Hugging Face Transformer library and can be literally used with a few lines of code. We expect that these resources will boost NLP research and applications for Greek, a language for which public NLP resources, especially for deep learning, are still scarce. Thanks for your attention.